Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today we've got Francois, who has just completed the course Linux Basics. So as we always do, we would want him to begin by showing his code base running on the real robot, and then after that we'll get into the details of what he did and the logic behind it. So let me now hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Francois.
Right. Hello everyone. So first of all, I'm gonna start by introducing myself. My name is Francois Gonothi Toure. I'm a research master's in computer science student at the University of Quebec in Montreal. And I'm working right now on like a master thesis, which is based on let me call it like embodied AI and robotics for animal welfare. So today, what I'm gonna be doing is to present my capstone project of the Linux for Robotics course from the construct. So I'm gonna start off by first of all making the code work on the real robot, and after that I'm going to follow up by making it probably work on the simulation if like I have some time for that. And after that I will try to explain the code, like what's the structure that I used to make it work.
Okay.
So basically what I'm going to start with is to first of all, when we look at the file structure here, we do have as it says. First of all, I'm going to start with this one here. So basically, after you're done with working with like the code on the real robot, what it asks you to do is to simulate it on the real robot. So first of all, we have this as you can see here. Let me just try to adjust this one a bit. Okay, so everything is actually inside this Linux basic project. So we're going to start off by first of all like okay, moving into this ROS workspace directory, and then in here we have like the install. So we can start off by first of all sourcing everything. So it's gonna be like source install setup.bash. And after we've done sourcing this one, we do the next thing is going to be moving inside like okay okay, we have to go into this folder like ROS2 and then source. Here we have this src, and then we have our Linux project directory in here. So everything is actually going to happen over here. So we have three main files. So the first one is going to be how to launch, first of all, the robot interface. So that's like a Python script. And then we do have two batch scripts. The first one being like the obstacle avoiding bash script. And then the second one, like to visualize sort of like the robot functions. So I'm going to start off by running, first of all, the robot interface. And then we have to wait for a few seconds just for it to say that okay, it's ready.
Are you
okay? Now it says.
are you
Yes,
are
please.
you doing this in the window that you're sharing at the moment? Because I do not see you do anything in the console. Do you have another console that's behind, or a second screen?
No, yeah, I'm having it set up, but like I'm doing it on the window that I'm sharing. I can stop the sharing and share it again.
Yes, try that, and then maybe it will refresh.
All right. Okay. Okay.
All
Is
right.
it working now?
Yeah, let's give it some time, a couple of seconds. I think it will. Okay, that's good. Now we can see. Yes.
Okay. Okay, sure. Sorry.
All right.
I
No,
didn't
it's
know
okay.
it wasn't like presenting over there.
Yeah,
Okay,
it's good.
so basically like we have this robot underscore interface.py file, which is like the Python script that like sort of launches the robot interface just for us to be ready to go. And then the next thing we're going to do is to launch a new code cell in which we're going to now launch the so I have to go into ROS underscore workspace. We go into the src directory, Linux again, and then we have this obstacle avoider bash. So that's what I'm going to launch right now. So I'm just gonna go like as it says here. So basically I'm just gonna go and do here dot slash I'm sorry, obstacle avoider, and then boom. We just have to wait for it, and it says set parameter successful, and now you will see the robot sort of moving, right? as you can see here on the real robot, the robot actually moves for like 0.29 meters, and then like it takes some time, so we can just like look at it, and it keeps going when it's okay. It has detected like an obstacle, so now it's going to make here a right. Okay, it says like turning left because it has detected an obstacle over here, and that's what it's going to do. Okay, now we see the robot like turning over here.
Can you enlarge that window a little bit more? Yeah, or
okay,
just drag
maybe
it
like
over, drag it over your IDE so that it's become okay. It's fine. That way is also good.
Yeah. Okay. So yeah, it's going to come over here, and then here also it's going to detect an obstacle over here because like it uses the lidar like ranges to detect obstacles and so on, and it makes decision based on like that, let me call it like proximity sensor. Then here it has detected this one again, so it's going to make I think yeah, that's a right turn, and it's going to move again. So okay.
All right.
What I can do is also like we can think drag the robot's position.
What's going on there? Is it trying to figure out where to turn,
Yeah,
or it's
absolutely
not turning enough?
Yeah, I think it's just trying to figure out where to turn.
Okay.
Okay, it's turning, so it's now okay, gonna move. Yeah.
Okay.
So, and yeah, here again, it's going to detect like there is a wall. This is a wall obstacle.
Yes.
So it's going to make a new decision and turn, I think, like right, and it will move forward again. This one. So it will make the turn. Yep.
Do you have a certain way of maybe telling which way it will turn, or it just chooses which?
No. It's actually based in the code. So like basically it detects like the obstacle and tries to make sure, okay, is it a right or a left turn that is like appropriate for the obstacle like that it has just detected.
Yes.
And it will turn like towards that path.
Okay.
Like for instance, here it's going to make the decision. Okay, now it has detected one again, and it's going to check. Okay, am I gonna turn left or right? And then yeah, it will check, and then it will just go this way.
All right. What threshold value did you use, and how close can you get to obstacles?
I think it was 0.300, I guess, for the threshold value.
0.3. Okay.
Yeah, 0.300. Okay, 0.3. And then it can get close, but like I don't want it. Like we don't actually want the robot to go, and bump into the obstacle.
Yes.
So it has to be like it shouldn't be close enough to the obstacle because like you should have some sort of security measure when you're doing.
Yeah, it should have some clearance. Yes.
No, absolutely. Yeah. Okay. So I can just minimize this window. So basically that's it for the robot working in on the real robot.
Right.
I don't know if I also have to show like it working in the simulation, or like that's something I can do too. Is that necessary?
I don't think so. Not at this point. I think we'd rather get into your scripts, right? So we want to see what you did, and you can explain some further detail that's not really apparent when the robot is doing the task.
Okay. So I didn't like make any presentations. I mean, like PowerPoint presentation, but I did make some notes and I printed them out and everything. So that's what I'm gonna be talking about. The first code that we always launch is first of all the robot interface. For the robot to be able to communicate with what we're doing here so far. So basically
I think
the program that follows.
You can stop the robot now. So you can stop your obstacle avoider script there. Yes. So that when we
Perfect. Okay. So as I was saying, this is the obstacle avoider code that is the main program that follows the wall. So like that's actually what I'm going to call the primary program responsible for obstacle avoidance and wall following in the bash script that I was just showing. So basically it uses 5 LiDAR scan. And then so we have like the first one is going to be left, front, and then like right. Okay, left, front, right, and then right. So these are the 5 LiDAR, scan inputs that actually it gets. And it also sort of implements an 8-case decision tree to make the robot movement. So basically, that's what we have, let's say in here for like the robot movement, because like it shouldn't just detect the obstacle and just stand over there. It has to move, and then it avoids collisions by checking proximity threshold, which is the question that you were asking before.
Yes.
Like it's 0.3 like meters. And then on top of that, it sort of executes like angular velocity by changing, the angular velocity sort of changes when obstacles are near. That's what we were saying in the simulation. Sorry, not simulation, on the real robot, like when it gets closer to the obstacle, and then like the angular velocity, which is like the turn that it makes, it changes over there. And then it sort of moves forward proportionally based on clearance distance, right?
Right.
On clearance distance. And now it sort of includes like recovery logic if the robot gets stuff like right turn left and stuff like that. So for the code explanation, the script uses, I didn't launch this one when I was doing it, the robot function, but like that's something I could have done too. But like basically, that's what was appearing here. So it's like the robot function. It's just gonna be like returning these parameters, like the math that is being done over here.
Okay. Can you? So before, I normally like to ask questions as we go. I hope you don't mind. So before we go any further, I want you to at least give us some background on how you ended up choosing 5 laser scan indexes to consider, right? So you've got left, front, front right, and right. So I'm assuming because you have all those being checked in your obstacle avoidance algorithms, right? Why did you choose to use all 5 and not like 3, for example, depending on the case? So just take us through the logic of that. Yes.
All right. So I think the logic behind this is basically it's just like to have a very good optimized, path planning and navigation. Because when it's limited, at some point maybe it will get into a certain situation, but it's a machine. It's not going to make decisions based on something you didn't tell it to do. So like basically when we look at the robot, like it has 2 wheels, right?
Yes.
And then it moves forward, and it has like the one in the front is not the wheel, but it just allows the robot to make the how is it called, like the circle
turn in place, yes,
movement, or like
it's a custom
absolutely
to support,
turn in place, or like absolutely.
Yes.
So basically, like when we look at the I'm just gonna drag this and drop it here. When we look at this, like here it is, right? And then okay, so basically let's say the robot is supposed to go this way, or maybe this way. It's not going to look backward, right? It's either front, it's just going like straight forward,
right,
and it's not moving backward, right? And then okay, we have moving straight forward, like it's going to the front, and then here it's the, let me call it the left of it,
right,
as per what I'm seeing here on my screen, and then here is the right. Right.
Yes.
And then we have over here that's going like to be the front left.
Right.
And then here is going to be the front. How is it called? Like the front right. Right.
Agreed.
Right, left, front left, front right. So without using all of these, like when the robot gets in position, like let's say it has gotten over here, and it does the scanning, and it doesn't have like, let's say okay, this is front left. It's going to make a bad decision, and then it might bump into the wall.
Okay.
Yeah, so that's the logic that I used, and that's the reason why I used those 5 laser scans.
Indexes. Okay. Oh, good. Yeah. That's very, very good actually, because the more you've got, the better it is at taking in consideration of things. But I also want to know, right, in relation to this, you will run into cases where your robot over rotates, right? So it rotates too much, and it ends up considering, like the clearance that it was supposed to get, it will end up not getting it, because you are like, let me say in quotes, oversampling, right? So how did you deal with that problem of controlling how much angular distance it covers, or for how long it turns?
I think that one is actually sort of based on like when you take this portion of the code from line 34 to I think let's see, yeah, 37, not 35 to 37, because like this one is just a comment.
Mm-hmm.
So first of all, it sort of calculates clearance, right? And based on the threshold, and
Mm-hmm.
it makes the decision.
All right. So
Okay.
you are. Sorry to cut you short. So if you're calculating clearance, are you
Mhm.
taking into consideration the angle and trying to multiply it by, or doing some trigonometry on it? Is that what you're saying?
Yeah, yeah, absolutely.
Okay. Okay. Can you show
Yeah.
me where that is happening? Because I think it's
Mhm.
very much possible to do, but it
Mhm.
gets complex, right? That's why I want to see where are you doing that,
Yeah.
and can you
Mhm.
explain a little bit more?
Okay. Okay. So here we go from let's say line 47 to 54. Basically, as you can see here, after we've done like the clearance calculation,
Mm.
so it tracks the repeated blockage, right? And like at some point when I was running the code onto the real robot, like here, it came until here. Like I think this is a break, right? And then it was like sort of moving. It took like several seconds before making the decision to turn either left or like all right. So like when it tracks the repeated blockage, what's going to happen now? It will launch this emergency recovery if it's stuck for too long.
Mm. Okay.
Okay, so here is now it sets like the command velocity, like the angular velocity to 0.6,
Mm-hmm.
and then it sleeps for like for three, I think this is like 300 milliseconds, I
Mm-hmm.
guess.
Okay.
And then it resets the angular velocity to zero
Mm-hmm.
now to make the decision. So this is the portion of the code that actually sort of deals with it.
Mm. Okay. So
And then now the
how did
the
you
lot.
choose the 3 seconds? Did you have to try and see how big the turn it makes, or you just picked it randomly? How did that work?
I think I picked it because like at some point, there is this joystick here, right, that you can sometimes use to reset, or let me not call it to move the robot to a certain position,
Yes.
right? But like when I did it at first, I think at some point it was bumping into the wall. Like that's when I was in simulation mode.
Mm-hmm.
And then at some point it would actually come onto what the wall is. And then yeah, so I was like, okay, I'm just gonna measure the angular velocity and see for how long it's going to work. So I did set it to 3, and I saw that yeah, that one actually sort of works perfectly well. So that's how I came up with
Oh, with
the
that value.
solution for it.
So
Yeah, absolutely.
you were
Yeah,
semi timing it to see how long it takes to make that rotation.
yeah, yeah,
Okay.
absolutely. Yeah,
Yeah, I
yeah.
like I like that
It was
method. It's
like, okay,
empirical, right?
today. Yeah, absolutely.
Yeah.
Today, w when I was running it onto the real robot, like basically it got stuck over here. It wasn't stuck, but like it took like several seconds right before making the decision.
Yeah,
But
we
like at
did
first when I
also
was doing it,
notice.
it
Yeah.
was going until here. Absolutely. It went I don't know if it's this way or this way, but like it was getting closer to the wall and it was bumping into it. But
Uh,
like that's when I was, building up the code.
okay. Okay.
So this one is just like for decision making logic. So basically it checks for clearance and everything. So it does a left turn and sets up the angular velocity to this value and does it. And then this other one for the right one, because like, we are in a 360 degree something. So either it turns left or like it's positive or negative value over here.
Mm.
I think yeah, basically that's it. And then the other ones I just so these are like the conditional statements for moving forward, turning left, and then deciding the direction based on like the input values that it's gotten from the navigation itself.
Mm. All right. All
Yeah.
right. So this is the obstacle avoidance script. So
Just to move on now, like maybe just give a very brief code explanation. So what I wrote down was that first of all okay, so the script processes like this robot underscore function uh, that is here, and then to sort of reuse robot interface commands, and it initializes the robot's motion to 0.
mm-hmm.
That's basically what it does. And after initializing it to 0, it sets the threshold to 0.3 meters, which is what we've already talked about.
Mm-hmm.
And the LiDAR sensor is going to scan values and read like using like the function wrappers, what I was showing in the beginning of the code, not here, but in the obstacle avoider.
Mm-hmm. Okay.
Yeah. So as you can see here, it sets everything to 0, 0 here, and then it sets the threshold, sorry, to 300 meters.
Mm-hmm.
Sorry, 0.300 meters. Yeah. And after that, based on now on the scan data, logical conditions actually sort of decide whether the robot, what I was talking about, is going to turn left or right, or if it's going to move forward.
Mm-hmm.
So that's actually based on the input values it's going to get from laser scans or like from the LiDAR scans. And then if the robot stays blocked for too long, then there is this emergency here recovery portion of the code that makes sure the robot is stuck. Now it has to,
actually terminate, or when to resort to recovery maneuvers like let's say reverse or do a complete 180-degree turn. How does that work, right? Are you just counting, or you are counting towards making a certain maneuver that will get it out of that stuck zone?
I think there is no value that I actually set and then said, okay, so if it reaches this value, the robot just has to stop because it's gotten stuck over there for too long.
Mm-hmm.
The ideal thing to do is, I would say, like sort of making the robot really make the decision and turn and make the turn, right? Because like that's what's ideal when you're being a roboticist or like working with, let me not call it autonomous robot for now, but like yeah. There is no way it's going to do that. So basically, we have these three things. It gets the clearance, and it tracks repeated blockage. Now, if it's blocked for too long, okay, by this one, then it's going to launch the emergency recovery. Yeah, but there is no like threshold, time threshold that it has to reach and then stop the robot completely.
Okay, so within the emergency recovery, I see that you're setting angular velocity to 0.6, right? So
that's like a 60-degree turn, actually.
Right. Okay. Yeah. Yes, that's what.
So it's like I'm doing 360 divided by 4.
All right. All right. So and you're hoping that after making that 10, the robot will be clear of whatever.
By 6. Sorry.
Okay. Okay.
Yeah. Yeah. Based on the setup that we have.
Yes, that's where I was going. That's what I wanted to understand. Does the emergency recovery actually do something before execute or incrementing the stack counter? So yes, thank you very much for explaining that.
Yeah, you're welcome.
All right, you can proceed. Do you have any other bits that you wanna speak about?
I think like probably I would just comment on the service that searches for wall. Like we have a wall search service in here.
Did you implement that yourself, or it's not really a requirement, but I want to know what led you to that.
Basically, like I was also making use of tools that we have nowadays to help you with the coding part, because like the most important part is you having the logic of how it's going to work, and then you have tools that also help you build up like what's going to like build up the instruction that you're going to pass on to the robot, basically.
Okay, so within that wall following implementation, what happens? Can you explain step by step what it is doing in order to be able to execute that wall following behavior, or to exhibit that behavior?
Just give me a second. Okay. So here it is. When we go through this decision logic, right? And then at first, like, it starts by setting everything to 0. And then the threshold is here. We talked about it already. The laser does the scans, and then it does some sort of basic sanity check. So one or more like scans are missing. Like if everything is not getting scanned, and it gets the clearance, it tracks like repeated blockage. It launches this one. Now the decision block is like based on what it's gotten from the clearance calculation, it's going to make the decision, right? Like whether it's going to turn left or not. And that's actually sort of controlled by this conditional statement, right? So if all directions are blocked, it has to choose like a new turning direction. Does it have to turn left? If that's the case, okay, if this one is verified, then it will turn left by setting like the angular velocity to this one, right? And then if it has to turn right, it's going to set angular velocity to minus, which is like the negative. Because like when we take how is it called in English again? In French, it's like repère orthonormé. Like we have 90 degree over here, and then the other side is like negative, and the other side is positive.
Alright.
So when it's turning this way, like the value has to be negative, and the other way, the value has to be positive. And then it does the sleep for like 1.5, and then it sets angular velocity to 0, and then it starts like reassessing like after turning again. And yeah, so what I was talking about right now is actually controlled by these conditional statements, actually. Yeah. Now it turns right over here, and then here it's going to move forward a bit, and then it checks again if there is no obstacle. If there is none, everything is clear, and it will keep moving forward. If there is an obstacle, then it has to know whether it has to turn left or right. Okay, when it gets to robot session has ended.
No, it's fine. It's fine. Just close.
Yeah. Okay. Basically, yeah, that's it. It's the wall search service, like actually follows just this one, these conditional statements for you.
Okay, so it's just a repetition of just that.
Yeah.
But did it show to actually do what you wanted it to do? As in, when you did test, was it able to actually follow the wall in a perfect way?
Yeah, it was. Yeah.
Okay. All right.
As you saw over here, but at first I didn't want to test it on the real robot because like I don't know, I didn't want to like mess up with it, right? And so I used simulation a lot with Gazebo and Alvis, making sure everything works fine before running it on the real robot. And that's what I always recommended. When you're working in robotics, always start with simulation, then end up with field trial or field implementation. So I made sure everything works in simulation first before doing it on the real robot.
Wonderful. Thank you so much, Francois. It's been a very nice presentation.
You're most welcome.
So congratulations. So just
should I stop the sharing?
Yes.
Should I stop the sharing?
Alright everyone, this was Francois' presentation, and congratulations to him. Would like to thank him for giving us such a detailed explanation, and would like to encourage all of those of you who would want to try this course or the other courses that we do offer certificates on to do so, and then you can come and showcase your work as well. We believe that you learn best when you teach others, so this is part of it. So until then, keep pushing your ROS learning.